Leibniz Institute for Plasma Science and Technology in Greifswald, and I'm also active here in the Energy Transition Alliance. And it's my honor to open today the session High-Tech Industry of this interdisciplinary conference, Energy Futures. Of course, this session today is more or less a little bit on the border of this interdisciplinary conference, which is a little bit more dominated by topics of social science, space science, and economy. Of course, the technical area of the energy transition is a huge area, and so it's a little bit difficult to illustrate this whole area here. It can be only an illustration by the topics, and but on the other hand, I'm very happy that we could attract speakers here from quite different topical areas. So we span a large area, a large range from wind energy, solar energy, also to fuel cells, electromobility, and also contributions to the power to X topic, including hydrogen technology, and also some special things for the interesting topic of conversion of carbon dioxide. So that's why I thank the speakers very much in advance, and I'd like to introduce our speakers here today. So we will have Thomas Schedel, which is a senior scientist at the Institute of Applied Energy Research of the Helmholtz Center, Berlin. We have Sebastian Wohlrab from the Leibniz Institute for Catalysis, Rostock. He's a group leader of inorganic functional materials there. I'm very happy that you are here, Bernd Abel, Director of the Chemical Department of the Leibniz Institute of Surface Engineering in Leipzig, and also Director of the Oswald Institute for Physical and Theoretical Chemistry of the University of Leipzig. I greet you, Frank Adam, you are the group leader of the offshore wind power at the University of Rostock. It's an honor for me because I'm also have a chair in Rostock here. And last but not least, my colleague from the Leibniz Institute for Plasma Science of Technology, Angela Kut, will have the last talk today. She is a speaker of the project Campfire, which might be known to some of you already. Yeah, that's why that is only my very short introduction, so that I'm happy that we will have many talks here for the different topics, and of course that will be examples, and I ask the speakers also to go not too much in the technical or scientific details here, but give more an overview. But that's also what I expect, what I saw from the contributions, that most of them are overview talks for the different topics. Yes, one hint to the audience also. There is a chat function here, which will be used so that you can place your questions in a written form there. So I will collect all these questions and will present them at the end of the talk. If a participant will become a speaker for the discussion, we can also arrange this from here. Yeah, then let us start. I will first ask Thomas Schedel to start with his talk. So the floor is yours. I will switch off my microphone now.
Okay. Mr. Ulan, maybe can you start the presentation?
No, I ask you to start the presentation from your content library. Yes, if you go to your content library, you have the presentation. There is this I symbol, and there you can start your presentation.
There's this I symbol. Yeah, it's a content library. I just had it on my screen, but now, yeah, okay, maybe it's there. Yeah, can you? Okay, so today I'd like to give some introduction into artificial photosynthesis, and these are here my issues. So we start with the state-of-the-art scientific and technological challenges and perspectives, and the basis of my talk was the outcome from, let's say, experts working in this field for 10 years. For example, in Rostock, we had this light-to-hydrogen project coordinated by Professor Bella, or this biology program running over 6 years from Professor Jägermann, Wolfram Jägermann, and you are invited to go to this artificial photosynthesis outcome paper. It's very interesting. So this is very clear, well known that the sun delivers to us a lot of energy every year, 10 to 18 kilowatt hours. Our world consumption is 4 times lower, so 10 to 12 times 160. And here in Germany, we had 360 roughly giga kilowatt hours. So I would like to concentrate today on the direct usage or utilization of sunlight to split water into hydrogen and oxygen. So there's a direct way here shown below on this right-hand side, the photoelectrochemical route and the multi-stage route via photovoltaic power station and coupled to electrolyzers. So astonishingly, if you look to the right-hand side, only 3% of fossil fuels are used for conversion into valuable products in chemistry, for example. And yeah, the other 97% is burned. And this is horrible from my point of view, because this fuels resources formed are over a million of years. And so situation is also reflected on the left-hand side, and 85% is provided by fossil energy carriers to have our world supply here for commercially traded energy. And in the next slide is shown that this is also reflected in Germany. So only 15% at 2 years ago, maybe it rose a little bit up, is coming from the renewable energy resources. So primary energy consumption in Germany is, as I said before, 360 giga kilowatt hours. Looking to the challenge now, this is coming from a very interesting, very recently published study from Agora Energiewende, from Progress and Wuppertal Institute and Öko Institute. You can have a look via the internet pages, and here shown the challenge, what should be go on if we have a climate neutral Germany in, let's say, 2050. And we start now with this 860 million tons CO2 equivalent, and this should be reduced respect to the emission of 1990 to 440 roughly millions of gigaton greenhouse gas emissions in let's say good 10 years. And the hydrogen in the energy industry plays here, or has to play, a big role, and also in industry, but also in the traffic. I will show you in this talk. So why is hydrogen such kind of very interesting fuel cell? Or you can have a look here to the energy per weight. So this is the energy density per weight, and compared the hydrogen, for example, at liquid tank or 200 bar pressure tank, compared to methane, there's a factor of roughly 2.4 higher energy density per weight. If you look to the energy density per volume, hydrogen should be compressed, and because the volume is very big. And it's only comparable to hydrogen in the liquid gas phase, and this is comparable to methane, natural gas, and this is by the way, a drawback. But nevertheless, if you look to compare to high performance battery cells from Tesla company, the energy density per weight is drastically a factor of 130 lower than compared to hydrogen. And only here the volume density is a little bit higher. So if you look to the state-of-the-art hydrogen, the resources today are steam reforming process of natural gas, roughly 50%. This is a high temperature process, up to 1000 degrees, depending on catalyst. And the refinery and chemical exhaust fumes are also resources, 30%. Coal gasification, 18%. Electrolysis of water is only 4%. And this should be a little bit increased. And I will show you in this talk how it can be done. And going now to electrolyzer, the principle is shown here. So the water is inletted here at the anode side and is oxidized at the anode side to oxygen. And this is shown here in the slide on the right-hand side. You have the anode where the water is oxidized, and the protons are diffusing through this polymer exchange membrane PEM to the cathode, and here they are reduced to hydrogen with the electrons. Catalysts which are used here at the anode and cathode side are really rare earths, metals, metal oxides, iridium, ruthenium dioxide, and iridium dioxide on the anode side, and platinum or alloys from platinum at the cathode side. So it should be, that's one big challenge, replaced. Now going to the artificial photosynthesis, and the photosynthesis itself, the biological system exists over 3 billion of years. So this is a quite long time to have a very sophisticated and tricky system. And the heart of this tricky system is you have this chlorophyll molecules in the leaves, and the sun is absorbed with these chlorophyll molecules, and then you have a charge separation. So you have the inner photo effect, so-called. Sunlight is absorbed, and you create in this material in the chlorophyll electrons for reduction reaction and holes for the oxidation reaction. So now go to the oxidation reaction. You have a water splitting complex here, and the water is oxidized to oxygen, while here the positive H ions are diffusing with the electrons to the other side. And this is very tricky and nice thing. And here CO2 is reduced by hydrogen, and CO2 is converted to organic compounds and cellular building blocks. So we have this very nice example, and now it has been adapted here in our artificial systems. You have this light absorption, let's say in a semiconductor, a p-n junction of, for example, silicon. You have the absorption of light, then the creation of electron and holes. And on the left-hand side, so you have an oxidation catalyst, which is, for example, ruthenium dioxide, and you have the oxidation reaction to oxygen, and this H plus are diffusing to the other side. And here you have the reduction catalyst. And the reduction means electrons plus H plus, for example, creates hydrogen. Or with CO2, you have the formation with the Sabatier process to methane, or with nitrogen to ammonia. So this is the challenge, or the basis of what is shown now in the next slide. We have the direct route, the photoelectrochemical route in the artificial photosynthesis, or the multi-stage route with photovoltaics covered with electrolyzers. And only you use sunlight, water, and carbon dioxide. These are the resources. So, and if you look here, you can directly produce hydrogen with these artificial systems. For example, to store it in gas grids. This is very simple. This is done in Hamburg, for example, in an electrolyzer. And also you can create building blocks, or directly ammonia with nitrogen from the air. For example, you can have with CO2 and the reaction with hydrogen, with the Sabatier process, you produce methane. Or you can produce methanol, which is the basis for propylene. And this is a building block for polymers here. So CO2 as a carbon resource for industrial plastic with the combination of hydrogen. This is very challenging. So you can create a lot of directly fuels and resources also, like hydrogen, ethylene, methane, or ammonia directly. These are the green areas, or the green areas means that they can be used in very well-known processes, for example, in agriculture or in chemical industry. So the next slide shows you a little bit more about the multi-stage artificial photosynthesis we can use commercially photovoltaic modules or power stations, and coupled it with this kind of PEM electrolyzer. And one big challenge is to reduce the voltage which is needed here for splitting water into oxygen and hydrogen. Normally, the electrochemical potential is at 1.32 3 volts, but you need some more voltage because you have a loss of energy and form to heat due to this diffusing of electrons in the electrolyte or the protons. So there's one big task to replace noble metal catalysts here on the PEM in the PEM analyzer electrolyzer by abundant materials like nickel, titanium dioxide, or something like this. So what is shown here, this is the state of the art. This is a 90% efficient device. This is called monolithic electrochemical device for direct water splitting from our colleagues, published with our colleagues. It was a big cooperation here with Freiburg people from and also US people at water. And what is the heart here is on the left-hand side, you can see this gallium indium arsenide, gallium indium phosphide tandem solar cells, so 2 solar cells produced by the illumination of light, some voltage, let's say 2 volt voltage, and some milliamps, so in the range of 20 milliamps. So you have a 40% efficient device roughly, and this is covered here on the front side with rhodium as a catalyst producing by sun illumination hydrogen, and in the rear side you have this ruthenium dioxide catalyst producing oxygen. And so this is the state of the art on a laboratory scale. Unfortunately, you have a problem of degradation here. So maybe it works for 100 hours. Degradation is a big issue in this field. Another more example is shown here, the integrated system for photoelectrochemical water splitting. The basis unit is they do this colleagues here from Jülich. They use tandem cells, so based on amorphous silicon and microcrystalline silicon, which is shown here on top, covered by a glass. So it's a standard module, and these people developed with or combined this standard module with the electrolyzer, and the basis units are shown here. This is a standard PEM electrolyzer for hydrogen and oxygen evolution reaction, and they can scale it up, in this case of 20 by 30 centimeter, and the efficiency is not high as much, but could be increased, and the efficiency is in this case roughly 4%. And this activities from our Jülich colleagues are embedded in the European project called PEXSys. Here, demonstration of solar hydrogen-driven production on a large-scale area up to 10 square meters should be realized, and the project runs for 4 years and ended end of last year, but maybe it runs a little bit longer. And here in our center in Helmholtz Center, Berlin, we use silicon solar cells with high efficiency up to 20%, and the module area is typically 2 square meters. You can scale it up to 10 square meters, no problem. If you couple it with an appropriate electrolyzer, you have this possibility to create solar hydrogen with this equipment. And here shown a little bit the concept. The PV produces this current who drives the voltage, who drives now the electrolyzer, and the efficiency, the solar to hydrogen conversion efficiency is, let's say, the current here, photovoltaic current times this splitting of water and times this rate of hydrogen generation in mole per second divided by the sunlight, and every square meter sunlight has 1000 watt. So this is coordinated by Sonia Kalin in our center from the PVComB Institute. I found in literature some very more promising and challenging activities. This is a very big European project coordinated from all Spanish people, and also some German partners are here involved. Running up to the middle of this year, and the idea here is to split water to obtain hydrogen and oxygen, and to couple it with CO2 to get fuels and chemicals. As I showed you before, this is a route of possible utilization of this solar fuels. And the idea is to have an artificial leaf on the laboratory scale. There's another project called Telegram, also a European project, which starts in these days, so end of 2020, for 4 years. And the idea is to have green ammonia cycles. So that means using photovoltaics and wind, the conversion with hydrogen and nitrogen and hydrogen gives you this ammonia, and this drives the fuel cells. And the objective of this kind of project, coordinated here by our colleagues in Catania and Sicilia, is to have on the laboratory scale a complete green cycle of ammonia, because of the ammonia production, which is responsible for the CO2 emission every year of 1 to 2%. So this is a very nice project, and I'm really happy to see Angela Krut here in the auditorium. And she is now giving, I'm really interested in this campfire project, which is presented in this session again. So one big thing is, we had here the company Linde, and together with the ITM Power company from UK, they developed the biggest PAM electrolyzer for green, producing green hydrogen in Leuna. So Leuna Brunner was the former GDR triangle, chemistry triangle, and there they will install next year a 24 megawatt electrolyzer producing a lot of green hydrogen. And Linde, by the way, built up a refilling station. And here the project will show that the 600 fuel cell driven buses can be tanked, and with this they drive 40 millions of kilometers each year, and they save 40,000 tons of CO2 each year. And this is, if you compare this to the value of 860 we had now emission of CO2 and greenhouse gases, this is 0.5%. It's 0.5%, but it's a way. And if you increase this by a factor of 100, then it's 5%, yeah, right? Then, or 10%, then it's 5%. So this is a very, very good message from my point of view. And coming back now to the climate neutral Germany, in, let's say, 30 years, there are the development of 3 different hydrogen-based energy supply infrastructures should be established here. In, you can have a look to, this is coming from the Agora Energiewende study, and hydrogen refilling stations, fast charging infrastructure, and also overheat line systems. So that means you can have the green hydrogen, also the supply of electricity power via the fuel cells. So at the end, what are the costs? That is also important. Supply cost at each end user from within the next 30 years should be decreased from 70 to 10 euro cent per kilowatt caloric value. So this is the energy density per rate. And with this outcome and with this big challenge and some ideas how to solve it, and some concrete studies which are presenting the responsible people in politics and economies with this kind of outline, I would like to talk to. Thanks for your attention. And this was my former team here, Light to Hydrogen team in the Helmholtz Center in Berlin-Wannsee. And thanks for your attention.
Thank you so much, Thomas Schiedel, also to give more this overview here. We have only time for a few questions. There's no question from the audience directly, but from our speaker, Frank Adam. So let me say, so he asked how long it will take probably to have maybe electrolyzers of this kind in the kind of 200 or 500 megawatt. And also he mentioned that there is the other way to use directly offshore wind energy, for example, to produce hydrogen as a big project in Ireland. So maybe so there will be always some competition. Maybe you can also a little bit comment on the perspectives.
I came from semiconductor industry and from photovoltaics, so I know that if you doubled your production, so by a factor of 2, the production is increased. You reduce the cost by 18% roughly. This is a common law in micro electronics and in photovoltaics and car industry. So if you would like to come to 200 megawatts, you can count out how many years you need or how much the production of electrolyzers. So we are now at 24 megawatt. So by a factor of 10, you need the increasement of, so it's a factor of 10, so double, so it's of 5. You need an increase of 5 times, right? And the cost reduction is it's enormous. You can calculate it by yourself. I would say you need some years, let's say 5 years roughly. And then with this law of doubling the production cost reduction of 18%, you come up to this 200 megawatt. I will not talk about 500 megawatt.
Okay.
This is only my idea to this point. I see it in photovoltaics. Photovoltaics starts with silicon photovoltaics with €3 per watt, and now we are at 50 euro cent per watt or 80 euro cent per watt. So it's a factor of roughly 6 or 7 bit lower. So it's within this last 10 years. So yeah. That's becoming cheap, and everybody available.
Yeah, unfortunately, we are a little bit tight in time here. So there's also another question from Bernd Abel about the degradation. That might be a very interesting technical question. I ask you to shift this question even to a personal discussion, which, by the way, is also possible in this conference here. No? You can make a meeting there afterwards, or we can make it also after the session here a little bit. That's why thank you very much again, Thomas Schedel. And I want to come to the next presentation of Sebastian Wohlrab. Also, the co-author Alexander Wotzka is present here. And I ask you to start with the next talk, the CO2 capture from air and its direct conversion.
Okay. I hope the slides
are always okay.
Visible. Okay. So yeah, thank you for this invitation. Yeah, our institute is also associated with the high-tech industry for energy futures. My name is Wohlrab from Rostock, and we see ourselves also as a link between basic research and industrial implementation. On the other hand, the institute also focuses since years on this energy sector, and I want to show you some insights in this carbon dioxide utilization today. Of course, there are efforts to decarbonize the energy sector, but in my opinion, this will not be 100% possible. So the question is about the carbon source of the future. Therefore, it makes perfect sense to give an overview on this topic, especially on the possibilities of catalysis. I recognize I have only in some 20 minutes of speaking time, so I will try to make it very brief. Sorry, and I will not go into detail, and I show only some examples from our Leibniz research. Okay, then next slide is here visible. This is a slide you will find in many textbooks or reviews and so on. Yeah, this is a current view on the possibilities of biomass utilization, and I do assume that most researchers in the field see the bioplatform chemicals, the biofuels, or other bioproducts as the central concern of their work. But the whole thing is argued with the keyword sustainability. But if you look at the central aspect of such a cycle, you realize that the bottleneck lies in the production of biomass, as Dr. Schedel said before. the productivity of plants actually is very low. This is the problem, and I will explain this a little bit later in detail. And the message of the slide is the diagram is questionable because I cannot draw a cursor now here, but the biomass production on the left-hand side, this is the bottleneck, and yeah, you will see why later. And also the argumentation that biomass can help to deliver energy in the future, it's probably not the case in the future of the mankind. Okay, next slide. Yeah, but also we at LICAT often tempted to see carbon sources as the resource of the future, or plant carbon as resource of the future. Certainly they will contribute to our energy needs, but they will not solve the problem. For example, you can use biogas, yeah, to generate molecules from carbon dioxide via plants. But when you use such biogas, 50% of the captured CO2 by the plant leaves the biogas plant as such as it leaves as CO2, and this is due to the nature of the fermentation process, which can be optimized using various methods, but these can only be used to a limited extent in the existing biogas plant. So we thought about conditioning of the biogas downstream, and what you can see on the left-hand side here, we look to the dry reforming possibility. Normally, it's such synthesis gas, which here you can see on the right-hand side, is used for Fischer-Tropsch alkanes or for methanol synthesis. It's normally produced by a steam reforming, or to a lesser extent by partial oxidation. But this synthesis gas can also be produced by the dry reforming, and here in LICAT we are looking to very long-term stable processes. We develop catalysts for this process to bring progress into the biogas utilization in the future. But as I said before, this will not really help to solve the energy problem, because here on this slide you see, normally this is animation, you see a green rectangle. This green rectangle is the mass of biocarbon which is harvested over 1 year from all over the world. Namely 56,400 million tons of carbon are harvested by plants. This is a very interesting graph. Compared to this, you have 4,900 million tons oil and 2,000 million tons gas. So normally you would think, okay, using biomolecules you can solve the problem of the world, but at the first sight this seems a little problem, but the matter is more complicated. 40% of the carbon captured by plants comes from agriculture, and fortunately, and this is the most important number on the slide, so 38.4% of the world's area is also filled with agricultural land. So if you want to solve, or if you want to harvest carbon by agriculture, you have to bring much more agricultural land over the whole world, and this is here shown in the next picture. Maybe you can solve the problem here. This is the black square, which represents oil consumption per year. I assume that all carbon compounds, except those needed for the chemical industry and those needed for aviation fuel, have been replaced by other renewable energies. First and foremost, battery technology maybe here, and hydrogen technologies. But then you have the fraction of chemical industry and aviation fuels. So the opportunity is now to reach the carbon capture using plants. Is it possible or not? And then here, this is the most important slide. It is not possible. So this is my message. Where is the most effective place for new agricultural land? This is, of course, you look at this map. It is all this red areas. This is Africa and South America, where the rainforests are, and it's simply not possible to sacrifice this rainforest and for carbon production. When you look to the numbers of Malaysia and Indonesia, where only 60 million tons of palm oil are produced per year. So you cannot solve the problem of our energy demand by plants. This is the message I want to mention here. Maybe you can overcome it with algae-based technologies, but we are here at LICAT are focusing on possibilities to harvest carbon from air by means of new materials. Okay, and this small diagram should just compare the situation. And by nature, you can harvest about 1,500 gram in maximum with a plant per square meter and year, 1.5 kilogram. And the question is, what can a material do? This is the question nowadays. Also, other companies and scientific groups are looking into this question. We here in the heterogeneous catalysis part simply have chosen a well-known catalyst. This is the serum zirconium oxide, which showed good success in the catalytic conversion of carbon dioxide. And the first step, the carbon dioxide of this catalytic process is absorbed and then converted. We have now tried this absorption step with CO2 from the air, and this also works. You can see it on the left diagram. The absorption step occurs within the first 1 or 2 hours in the experiment, and depending on the temperature, the absorption capacity varies, being the highest around at 70 degrees C. Okay, after certain holding time, the CO2 can be dissolved, and if this absorption capacity is transformed into an absorber volume and normalized to time, and if catalytic processing also is included, then you can assume absorption capacity of over 1,000 kilogram per cubic meter. Compared to this carbon fixation by plants, it's quite a lot. It's quite good, and I also want to be honest. There are systems available. They are much more efficient. These are amine systems. They are more than 10 times efficient than our inorganic material, but our inorganic material is stable over that time. The amine systems are not so long-term stable. Nevertheless, there's a Swiss company called Climeworks. They also implemented a carbon capture unit on their fabrication hall. You can find it in the internet. You can see this very well. But we are a catalysis institute, and we raise more questions what to do with the captured carbon dioxide. And there are 2 possibilities. You can either keep the carbon in the oxidation state as it is, +4. This is the case for this molecule I show here, the dialkyl carbonate, the dimethyl carbonate, for instance. You can use it as a fuel. Such a molecule is very interesting because this molecule contains a lot of oxygen, and when it is burned, it releases no soot, so it is nearly free of any particles in the of gas. This is also what we have done the last years. I assume every one of you remember the esterification reaction quite well, and I want to show you here how this works. It's quite simple. You have in the first step on the upper left the absorption of a methanol on a hydroxy function of a acidic side. You create a met oxide, this methoxide is then is reacted to the carbon dioxide, which is previously absorbed at the basic side of the material. It inserts into the bond of the methoxide. It forms a monomethyl carbonate, and this is then further reacted with a methanol to the dimethyl carbonate. This is just to show what catalysis is. Then you have the desorption and the release. Okay, and we also focused on this reaction the last years. I have to be honest, we achieve yields of 1 to 2% maybe. This is too low. Nevertheless, we could increase the performance of a typical batch reaction just by phosphate modification, or we were also the first who did it in the continuous mode. It's also very interesting. We can reach equilibrium of this reaction within the first 3 or 4 seconds. This is also a very interesting thing. What we also do is here the use of membranes in order to shift equilibrium of this reaction to remove the product. This can help to increase productivity. But all in all, this reaction is not sufficient enough, and that's why I created this take-home slide message. I don't know how to call. There are 3 molecules which are really in the focus of research, also in our institute. There's all the C1 oxygenates, methanol, and formic acid, but also the methane. All of them can be used as hydrogen storage material. Methane and methanol can be used directly as fuel. The methane can be put in the gas grid. The methanol can be used as a liquid fuel in a tank. But also the formic acid is quite interesting, as I will show you later. Okay, and now I will present some aspects on these molecules. First, the methanation. Maybe this is the most prominent reaction. There are some plants, the Audi plant and Werle, for instance. What is the purpose behind methanation? The hydrogen which comes from the electrolyzer can be stored in the carbon dioxide by transferring the carbon dioxide to methane. The problem of this reaction is you always create 2 water molecules and you lose the hydrogen. Nevertheless, this system or this concept is realized in several stages. You need to separate the water from the methane, then you can store the methane and put into the grid or create power. What we did with Excitron was kind of scale up, and also this you see in the middle, the CO2 separation and storage. So we keep the CO2 in the cycle. And what we did here at LICAT is a simple upscaling of an existing method. We started with 1 to 4 milliliter catalysts and scaled it up to 500 normaliters per hour. So this was our task. It was successful, and Excitron is now building their apparatuses for a centralized energy supply. Methanol, for me, much more interesting. If you want to produce methanol from carbon dioxide, you are initially faced with a thermodynamic problem. You can see on the very left side on the slide, there's a calculation how the equilibrium behaves in dependence of removed water. So we calculated what happens with the equilibrium when we can remove water. And what we found, when we can remove water for 100%, we can increase the methanol yield to nearly 60%. And this brought us to a new concept or a new project idea. We use, for the first time worldwide, we use now porous membranes to remove the water at 50 bars. This is very, very tricky because you cannot really seal the membranes. It's difficult enough. And furthermore, we also supply the hydrogen along the membrane. This means we can Here on the right-hand side, we can feed the catalyst bed with hydrogen permanently. We can increase the selectivity of the process, but also the productivity at the reaction or a reactor outlet. I have to speed up. And what we did here is a catalyst screening. We used the conventional copper zinc catalysts, which are known from literature. We choose different kind of compositions and preparation methods. And now we are in the modeling stage. We could show first by modeling that this concept works. Next week we want to start the reactor. I hope I can update you when you are interested. I can show you more results in the next weeks. But now, when you have the methanol from the carbon dioxide created, what they do? You can, of course, burn it. You can burn it away. You can create carbon dioxide and water, but then you lose the hydrogen. Maybe the hydrogen you need for a fuel cell. And this is a work from Henrik Junge from our institute, and Matthias Beller. They found a catalyst, and compared to the state-of-the-art catalyst, this catalyst is very, very trend-setting because it works below 100 degrees C for the reforming of the methanol. Reforming means you can produce hydrogen from the methanol by creating carbon dioxide via this consecutive reforming steps shown on this slide. And they achieved also a very low carbon monoxide selectivity, and this is quite interesting for fuel cell technologies at low temperatures. The PEM fuel cells, for instance, below 100 degrees C and low carbon dioxide content. This is quite interesting for fuel cell technology. That's why also the University of Erlangen, they said, okay, let's support this catalyst. They use a porous material, bring some ionic liquids in this porous channels, and in this ionic liquid, you can see here this homogeneous complex is immobilized, and the reaction occurs on with ongoing time, and this is also done with a very high selectivity and long-term stability shown on this slide. For 350 hours, you have a nearly 100% CO2 selectivity. It's important for the fuel cells, but also a sufficient turnover over time. And here in the lower diagram, they connected this methanol reforming with a fuel cell and showed how the power generation can be realized by a pre-reforming step. And now
we run a little bit out of time. Yes, I ask you to.
Yeah, we have two slides, but these are important slides. Because I like this molecule very much, because this is also a take-home message here. You see a molecule in this scheme. It's formic acid, and when you do the hydrogenation of carbon dioxide, you end up in formic acid without loss of hydrogen because you do not produce water. This is very, very interesting and very important to know. I skip all these facts about formic acid, but show you our idea what to do with this concept. We want to create a hydrogen battery. In this hydrogen battery, you can store and release hydrogen by simply hydrogenation of carbon dioxide and then decomposition of the same, and keeping carbon dioxide in the system. This is the plan, where we now actually build up a prototype of such a hydrogen battery here in close by to Rostock, in Rostock Lager. And that's it in perspective. I tried to convince you a little about carbon dioxide harvesting. We will run out of carbon in the future, and the way to harvest carbon via plants is simply not possible. We do not have enough space on the Earth for this purpose. We can reduce our carbon consumption, but in the end we need some, and in my opinion we need carbon dioxide from the air. And then I showed you this 3 molecules: methane, methanol, formic acid. And keep in mind, gas grid injection with methane, methanol is a liquid fuel in the formic acid. I hope I can show you later in the next 1 or 2 years the hydrogen battery as a product together with our industry partner. I hope to do so. I hope I have not promised too much. So that's it, Professor Orland. Sorry for that.
Yes, thank you so much, Sebastian Wohrer, for this wonderful overview. I think I enjoyed very much that you present also many different pathways of the CO2 conversion in combination with the hydrogen technology. Unfortunately, we run a little bit out of time here. There are no questions from the audience. That's why I only want to ask: are there urgent questions from the other speakers, maybe? So if this is not the case, I will come to
yes.
the... Yeah.
I just have a question.
Yeah.
Thanks very much to your presentation. I know Heine Junge and Matthias.
Yeah, I know you know each other.
Yeah. I like to ask you very simple, maybe, what are the active sites for this formic acid reaction you showed in the last slide? So the hydrogen battery. Do you have any idea what are the active sites? So acidic side?
No. It's you can use different catalysts, ruthenium catalysts, for instance, and the thing is, these homogeneous systems are very fast, and for industrialization, I think we have to also heterogenize this kind of type of catalyst because of stability reasons.
Okay.
And the active site is the metal together with the ligand stabilization, of course.
Okay. Yeah.
Yeah, thank you so much again. Now I want already to hand over to Bernd Abel, and coming to the topic of fuel cells. Of course, there's meanwhile a huge variety of research on fuel cells, different kinds of this. So here the topic is solid acid fuel cell, and the floor is yours.
All right, so can you see my transparencies? And more importantly, can you hear me?
All okay.
Okay, so I just tried to get some sort of pointer here. Can you see my pointer? No. Or no.
This is indeed the problem. I want
okay, this might work. Okay, so I can erase that. Okay, so hello everybody. Before I start, let me thank the organizer for putting up such a nice, let's say, meeting within a meeting, and hope we get enough guests just from the general audience, maybe to appreciate what we are doing. So we are a little bit aside and really working on the details, not on the global things. We believe that we all can save the world, but it's the question if we do with our technical approaches. So in principle, everyone wants to have a car instead of a diesel that uses hydrogen and with just water on its exhaust. And it would be nice to really run a car on hydrogen. And that's, of course, the goal, but hydrogen may be a little bit far in the future. So due to various reasons. So hydrogen needs a grid, and it needs infrastructure and so on, which we at the moment don't have that much. Technology-wise, there are nice approaches, but it is usually nicer to have something that you can put as a liquid in your tank, for example, methanol and so on, and use it as a storage compound. So use power to X and then using something that you can fill into your car instead of hydrogen. Then you don't face all these losses and so on and so on. And then by reforming, you just get the hydrogen back, and then you can run a fuel cell. And that is pretty much an approach which is feasible, and it's on a shorter time scale, and maybe even a bridge technology. So, and at IOM, we are a surface science institute, so we are dealing with functionalized surfaces and also surfaces that are relevant for electrochemical devices. So, all right. So the motivation is we all face a climate change, and that's really one of the most important problems. And if you see, there is a demand just to, if you look at the energy demand in the future, that we are getting away from, I would say, oil, getting into solar and wind, into renewable sources. This is quite nice, and especially Germany is on the way of really having this Energiewende. But there is a problem with this because renewable energies and concepts have drawbacks. So usually, they provide energy when it's not needed, or they provide energy where it's not needed. So you need something to store the energy in principle and transport the energy. And this could be hydrogen, for example, or power to X in general, molecules that have built-in hydrogen yet that you can release. And the transformation device might be fuel cells, for example. And that's in principle our approach. So talking about fuel cells, you all know fuel cells already in operation. There are PEM fuel cells, which are in principle at the lower temperature side, and solid oxide fuel cells that are at the high temperature range. I will call them cold fuel cells and hot fuel cells in the following. The cold fuel cells have an advantage, fast start-stop operation, low temperature, but on the other hand, they need really ultra-pure fuel in order not to poison the catalyst. And the hot fuel cells, they have a very high efficiency. Poison resistance is quite high, and fuel flexibility is also quite good. On the other hand, they operate at quite high temperatures. So, and there's an intermediate temperature fuel cell, the phosphoric acid fuel cells, for example. They work at intermediate temperatures, they have a high efficiency, but on the other hand, they are highly corrosive. And that's due to the highly corrosive electrolyte phosphoric acid. And there's a sweet spot in between, which uses a solid electrolyte, solid acid fuel cells. And I will show you in a minute what these are. These are salts of these phosphoric acids. And they use one feature which is really interesting. Any salt of a phosphoric acid has no real function, but special salts, cesium dihydrogen phosphate, for example, has a superprotonic phase above 200 centigrades, and there it shows very good proton conduction. And these then work at intermediate temperatures. They have a high efficiency. Fuel is flexible, fast start-stop operation. Still, there are problems with the catalyst because the current approaches use a lot of catalyst. And at the moment, because they are still under development, it's a low to medium power density. So that is the point. And we focused here on these kinds of solid acid fuel cells, not to mess up with solid oxide fuel cells. All right, so there are there's one company worldwide, SAF Cell, starting to commercialize these solid acid fuel cells. These are really small systems, 50-watt systems. This is almost nothing. It's quite heavy. It's using platinum, and it's used as a zero-emission oil well control system. So it's decentralized technology, and in principle it works. And there's a follow-up, in principle, a military system also sold by this company in Pasadena. which is somewhat larger. But in principle, there's no real reason why one cannot make this bigger and use that, for example, in a car or so, because that's really the target, if you remember my first transparency. So in summary, it's nice progress on these new devices using a solid electrolyte, but this is basically at the moment a niche market, and it's still quite expensive. And well, what we would like to have is these kinds of fuel cells at the right dimension also in cars. Of course, you all know that there are cars that use hydrogen fuel cells, and there's a tiny market, in principle made up by Toyota's Mirai, and Hyundai has a model named Nexo, and yeah, also Honda is working on a car like that. So these are plugless cars and alternatives to the battery electric cousins. And but the number they have sold or leased is quite low at the moment. And the question is, what is the showstopper here? What is limiting the whole thing? And basically, it is reliability. So it is degradation and just the time you can use it. It's catalysts and so on. But it's the how you can use these. You don't want to have corrosive elements, and you basically want to have something close to a battery, which works reliably. And well, yeah, that's where solid acid fuel cells could help. So the simple operating principle is, so because I expected some general audience here, I left most of the equations out, I left most of the little details out, but just to get you an impression, how does a fuel cell work? A fuel cell contains of basically yeah, a device where you can combine oxygen and hydrogen in a controlled way. If you don't control that, you have an explosion. So in principle, you need two electrodes, in principle an anode and a cathode. Anode is the oxidation, cathode is the reduction. And in principle, a porous electrode on both sides that yeah, enable a controlled oxidation and reduction. And if you look at the equations here, you see that protons have to be exchanged, and therefore that you need an electrolyte, which is gas tight, and in principle separating these two gas phases. And then if you operate it in a way, you can get yeah, a current and a voltage on this. And the most important thing is here on the right side, it is all about triple phase boundaries. So solid acid or any fuel cell works on this triple phase boundary, especially the solid acid fuel cells. So it is the interface between the electrolyte, the gas, of course, and the current collector, which is in principle the electrode with the catalyst and yeah, as the name says, the current collector. And here on this interface, the action is happening, and that is in principle the point. And as you may see, the dimensions matter. So the dimensions, the micro and nanostructure matters for the electrolyte and the catalyst and the porosity of the electrodes. And that is what we are busy with at IOM, because that is functionalized surfaces, and that's in principle our business, and that's where we can make these things better. And yeah, so state-of-the-art power electrodes provide at the moment already quite high power densities. And as you see here on this transparency, this is an electron micrograph here in high resolution. Definitely the structure, the porosity, the nanostructure or microstructure matters. If you compress the phases significantly, that's in principle good for mechanical stability, but on the other hand, the porosity has to be in a decent that you get gas through. So really the micro and nanostructure really matters in this case, and it has been shown also by us that this cesium dihydrogen phosphate, which is the in principle, the salt or the electrolyte, which shows the superprotonic phase at high temperatures, good proton conductivity, and that these networks can often become the limiting factor. So whether this is nanoscale or microscale, porous or non-porous, and so on, and that's what we are working at. So this is dimensions of the phases close to this oxidation and redox reactions of hydrogen and oxygen. Oops. All right. So, all right. And how we do these things? You can simply say, okay, this is the salt in principle you can get by precipitation. But how we do it, we press it really in a several kilobar let's say press, and we make these pellets, and then we coat it by spray coating the pellet with a porous electrolyte layer. And then we deposit platinum on it, so we get a sandwich or a structure which is quite dense in the middle, so it's gas tight, and it has in the yellow and orange regions here the porous electrolyte deposited with spray drying with a spray dryer set up, and on top of it you have the catalyst, and this is done with a nanospray dryer shown here. And well, on the other hand, we also make it mechanically stable using polymers, but I'm not going in detail here on that. So that's the standard procedure, and then you can do impedance measurements, check if your pellet is really nice and if it works, and so on. All right, so we also involve theory together with Sebastiani in Halle. This is where theory meets even engineering. So we try to model. This superprotonic phase, this electrolyte, and so on, and try to understand why it is working, if it works, or why it's not working, if it's not working. So I'm not going into details here. Everyone probably thinks these are systems much too high, but they can be analyzed just with theory, and theory can help here in order to, or can help the engineers to get the best settings. All right, so so that is about the scales of the involved, I would say, phases. So electrolytes, electrodes, catalysts, and so on. One of the problems is, as you may all know, is the poisoning or the corrosion of the catalyst, especially if you are using phosphoric acid. It's simply deactivating, let's say, platinum, for example. And what we found out very recently is, which we just publish, is that if you use, let's say, a multi-layer graphene and put your platinum catalyst on it, and if you separate the catalyst from the electrolyte, which is exactly doing this poisoning and corrosion, then you have a much better performance. And we discovered that even, which nobody had expected before, that multi-layer graphene is a proton conductor and an electron conductor at the same time, which is quite nice. So you can separate the catalyst from the electrolyte and at the same time have these triple phase boundaries, because this new material is sort of mediating because it takes the photons where they are used, and in principle you have enough cracks and so on just to get the gas still through. So that's a quite nice trick, and you can do it both ways. You do these kind of Oreo cookie things, which is the pellet here, and this is the carbon paper. Then you have the graphene multi-layer, and then the platinum sputtered on it. You can sputter it just by sputtering techniques, then you have a thin film, or you can use ALD, atomic layer deposition, where you have clusters on top of the graphene multi-layer, which is even more efficient. So this ALD works even better than making thin films for various reasons. I cannot go into detail here. So this shows different cycle ALD results. And the nice thing is that you not just have a coating here, but also a porosity that helps you just getting the right porosity and just getting the right electron conductivity and proton conductivity. So that's the trick. So it's about to be published. Manuscript is just submitted. And of course, we can do test setups. We can measure current densities. We can measure stabilities. And of course, this is done by impedance spectroscopy. I don't want to go into details, but it is not just based on belief how these things are working, as I showed you here. So we can definitely measure these things. And what we saw is a proof of principle that graphene multilayer protects and separates catalysts from the electrolyte. And that's really a performance improvement. And that will help us one more step into the direction of getting these things maybe into cars. And then I think 1.5 years ago, I met Angela Krut when she gave a talk in our institute, and then we got into touch and discussed, oh, fuel cells. Okay, why can't one run fuel cells with ammonia? So as I told you, it is not so much about hydrogen and oxygen. It is about the feasibility to use a fuel. And hydrogen, you know all the problems. I don't have to teach you what the problems are with hydrogen storage, losses of energy, adsorption, and so on and so on. So ammonia is a nice, I would say, reservoir for hydrogen. And with reforming, you can just release hydrogen. And that is, in principle, the idea, to have, in principle, a fuel cell that has already an operating temperature, which can be used for reforming of ammonia. So this, unfortunately, doesn't very well work with PEM fuel cells, but at higher temperatures, this works. So the idea is ammonia reforming and operation temperature of a fuel cell. And yeah, that could be something for the future. What I advertise sometimes as an all solid state, in principle, fuel cell. And people want to do it with batteries, lithium-ion batteries. They want to have solid electrolytes. And in principle, I think the future is also in fuel cells, not having these punky phosphoric acid things that you have to seal and so on. It's nicer to have an all solid state device in that case. All right, so together with my colleague Wartmann, well, it's the deal to really do or solve a microfluidic problem. As you see, you have to make these bipolar plates. If you don't know what that is, it doesn't matter. So if you want to make a fuel cell, it's not just simply one device with oxygen and hydrogen going in and water out. So usually you have to have multi-stacks, and these are arranged in a way that we call bipolar stacks, and it consists of many microfluidic channels, in principle for taking the gases in and taking the water out and so on. But this has to be sealed, and this is a really difficult engineering problem. And that's where we have these experts in the Wartmann group. All right, so it's all about the nanostructure, as I said. The dense electrolyte, the porous electrode on top, and the catalyst on top of that. So as I showed you, the nanostructure and the microstructure really matter, and it's really even important to have a match of both. It doesn't matter, it's not useful if one is small and one is big or so. There really has to be a matching. And I try to get you the picture. What matters here most is, if we want to get this into a car, we have to have a larger diameter of a fuel cell, of course stacks. So the goal is making pellets with a large diameter here, and at the same time very thin. So that makes it very demanding in terms of stability and so on. And we have to avoid catalyst corrosion, which we are about to do with the help of our colleagues. And yeah, with this goal, I think, and these tools in hands and the recipes that we found out over the past 5 years or so, I think we are in a good position to really tackle the future that might come close, and the dream comes close that I was advertising in the beginning. There are already first hydrogen cars that run on ammonia in Australia. Here's an example for that. But with these new modules, not ready right now, but maybe in a few years, we probably come close to the dream that fits pretty much to our conference here, that we are sort of using sunlight, wind energy, power to X for water splitting, and ammonia synthesis, and using this as a nice, in principle, reservoir for driving fuel cells. So I believe it's already the nicest introduction for Frau Kut, so she can probably pick up on this. So yeah, that's my message. In principle, these things have to be improved. They are not showstoppers, but they have to be improved. They have to be reliable, and yeah, it's important to have the size and have the reliability to put it into cars, into decentralized cars that can be part of a power grid, and so on and so on. But in any case, it's a nice bridging technology before the real hydrogen comes. All right, so that's my end. Before I quit, I would like to acknowledge contributions of my group, of my co-workers here, and especially also in our new project, Jens Wartmann and Angela Kut, and our external collaborators in Russia. And yeah, that's about it. I hope it was not too specialized and not losing too many of the general audience, but yeah. Thanks for listening, and I'm ready to take any questions. Hopefully I was staying somewhat in time.
Yeah, thank you so much, Bernd Abel, for this very interesting and fascinating talk for me. In fact, we have only 40 minutes left here, so we are a little bit tight in time. But nevertheless, is there an urgent question, maybe from the speakers? It's not the case. Maybe there's a short question from my side. To use methanol, especially green methanol, would be very attractive from my point of view. How sensitive such a fuel cell is for contaminations, especially in water, if you have a mixture of water and methanol?
Yeah, water is not so much of a problem actually for solid acid fuel cells, because you have a water management anyway. So water is actually, other things are much more severe, but water I think is not the problem, because you have to mix up water anyway in the feed gases.
Yeah, but that might be a very nice point, especially.
Okay. Well, we were discussing that, but my colleagues didn't want to have any methanol really, and in our project we skipped that, because I think the idea to run it with ammonia would be quite nice. But of course, yeah, methanol is maybe a good test candidate before, and maybe we should stay in contact just to discuss these things.
Okay. Thank you so much. I will quickly come to a quite different topic. We will leave for a moment now the chemistry a little bit, and I want to ask Frank Adam to say some words about wind energy, especially offshore wind energy. I don't know if you're going to give the presentation in German or in English. I think it's more or less free, because most of our audience is in German, so you can make it as you like.
I prepared the English presentation, so meaning I will also speak in English as my previous speakers.
All others to switch off the microphone.
Okay, so first question, can everybody see my screen? Perfect. So then I will start with the presentation. Yeah, as already mentioned, so my presentation is on offshore wind mostly. And the main focus will be on floating offshore wind, where we are. So the state of the art will be presented, the challenges, but also the solutions which we can provide with floating offshore wind. And I was very happy to see also that the previous speakers discuss storaging, energy, etc. So because I'm coming more from the provision side, so I'm providing electricity for all those nice storaging technologies. So the content of the speech is, first of all, I would like to give a very quick introduction of the chair, then the state-of-the-art overview of floating offshore wind, chances, challenges, and also solutions will be presented, and in the end, a summary will be shown. But you see already here on the on the right-hand side, the part of UK, especially Scotland, where blue-colored areas are highlighted. And especially those areas are at the moment under lease. So meaning developers, wind park developers and or future operators are bidding at the moment in Scotland to erect and start with the operation of offshore wind of around about 8 up to 10 megawatt in 2026 up to 2030. Whereas I would like to highlight most of those areas are in water depth with more than 60-meter water depth. So meaning most of those areas are for floating offshore wind and not longer for fixed. Okay, to the introduction of our chair. So our chair was funded in 2024. The head of the chair is Professor Uwe Ritschl. We are doing research mostly in the field of wind energy technology, offshore but also onshore. But some of our colleagues are also working in the field of sector coupling, more or less from the electricity provision and also the technology, wind energy technology point of view. Highlight on my personal introduction. So beside my university background, I'm also working at a company. So I'm having 2 employers in the end. So I having 1 feet in the industry. I'm working for a consulting and engineering company with around about 350 employees, and I'm working also for the university, which is quite nice because I never lose the, the perspective of the industry during my research, especially also at the university, which is very important, especially for an engineer. Okay, now back to the technology itself, back to floating offshore wind and the state of the art. Before I would like to give you an overview on the state of the art, I would like to highlight a bit the technology, and also I would like to provide you definitions, because often people are mixing definitions and wordings, and I would not like to do that too. I would like to highlight here the wording as per the standards. So we have floating offshore wind, so meaning we have a wind turbine. Wind turbine means the rotor nacelle assembly, and then we have the complete support structure, and support structure meaning the tower, the substructure, which is which can be floating, which can be fixed, and the foundation. And the foundation is a structure which is in or directly on top of the soil. So if someone is saying to you, I have a floating foundation, per default, this is not possible, because a floating foundation, so a foundation cannot really float. A foundation is an anchor or something like that. With regard to a floating solution, there is a bit different to fixed offshore solutions. So you can see here 2 typical floating solutions. The only different from a definition point of view to fixed is those floaters are they can move freely in the water, so they have degrees of freedom higher than 0, indifferent to fixed, and an additional component need to be considered. This component, or those components, are the so-called mooring lines, which are the component between the substructure and the foundation at the soil. The reason why floating becomes more and more important for offshore wind is they are more cost competitive in deeper water than fixed solutions. This is quite simple to describe, because the if you go to deep water with a fixed solution, you need more material to bring the solution and also to fix the substructure with the foundation at the soil. So meaning floating solutions are cheaper in deeper water. And the nice thing is also that once you're going into deeper water, normally you are also going far away from the coastline, which indicates also higher and also more constant wind velocities. So meaning the annual energy production of floating offshore wind is per default or can be higher than for fixed offshore wind, which is closer to shore in shallower water. In addition, there are some advantages indifferent to fixed, especially you can have a type certificate as you have it for an offshore wind turbine. So meaning substructures can be type certificated, which reduce costs as well, and which brings you also in the position that you can go, for example, to your engineering company or to a substructure provider requesting a specific solution, a specific substructure, and those guys can offer you directly a solution which is already on the table and can be erected within a very short time. And also, and this is quite important from my understanding, the environmental impact of floating solutions are less than fixed solutions because no driving or no pile driving is needed. So you have no noise emission to the water, to the environment, and also a decommissioning, a 100% decommissioning of floating solutions is possible, indifferent to fixed. Normally, for fixed solutions, part of the piles are still in place even after decommissioning. So those nice piles will be still in place after the turbine/the wind park is decommissioned. When we are talking about floating offshore wind, we are talking about 3 different stabilization mechanisms. So the first one, it's a gravity stabilized solution, which you mostly know from buoys. So if you have seen a buoy offshore, this stabilization mechanism is the same as for the gravity stabilized solution. So you have an long pile under the waterline, which has a low center of gravity, and this low center of gravity stabilizes the whole system in that way that this system is stable for nearly each for most of the offshore conditions, or for all offshore conditions, because it's stable per default. Then we have a buoyancy stabilized solution. The buoyancy stabilized solution is similar to a ship, so it's stabilized in the same way as a ship is stabilized. So if an inclination of the ship is if the ship is inclined, you have a buoyancy force on one side, and this buoyancy force brings you an up and moment, which brings the ship back into the position of the equilibrium. So this is a buoyancy stabilized solution. And last but not least, the mooring line stabilized solution. It's a solution where the whole structure is pulled underwater. So meaning you have more buoyancy indifferent to the gravity force. So it's like you are bringing an empty bottle underwater. So you have a high buoyancy force there, but you don't leave the bottle there without any mooring lines. So you are attaching mooring lines to this structure, and this stabilizes the whole system in place. And this last solution, especially the mooring line stabilized solution, is the solution with less motions indifferent to the other twos. So the next slide, I highlighted this already on the slide before. That's the reason why I would like to skip it and going directly to this slide where you have an overview of floating offshore wind, which was first, or where the first substructure was commissioned in 2008. So it was a 200 kilowatt device, a 2-blade wind turbine on top. And after 2008, a lot of different substructures from different developers were installed. So with a substructure from Equinor, a big oil and gas company, which is going the path to become a renewable energy producer in the near future. So we have Principal Power with their semi-submersible, with their buoyancy stabilized solution in 2011, etc., etc. Especially the Japanese guys were very active after Fukushima. So they brought a lot of floating solutions into the water to produce offshore or to convert offshore wind to electricity with their wind turbines. And since 2017, the first floating offshore wind park is under operation in Scotland. So it's a 30 megawatt wind farm, and the next wind farms are following. So especially in Norway, a wind farm, the so-called Hywind Tampen project, is under production already. And we will see there 10 megawatt wind turbines in the near future in Norway. With regard to the chances, challenges, and also solutions. So when we are looking to the global wind market, when we are looking to the demands of the industry and also the countries, we see that there is a need, and there is also a willingness to increase the number of offshore installed wind turbines in the next decades. And we see here the trend, which was published by the European Energy Agency. And there's one important thing I would like to highlight. So in the end, we need to commission around about 30 gigawatt per year in the next years to reach these aims. And to do that, a huge amount of floating offshore wind is also needed, because the areas in shallow waters are less than in deep waters. And the trend for, sorry, my son is coming home. So the trend in floating offshore wind is seen here. So we can expect roundabout 70 gigawatt until 2040 in the European oceans, North America, and also Asia, whereas Europe and Asia are the core markets with regard to floating offshore wind. Another slide presents you the core sectors, and especially also the areas with a highlight here on Europe. So meaning you see a high potential on deep water areas and a need to bring floating offshore wind into the water to produce offshore electricity from floating offshore wind. But there are also challenges, especially with regard to the level size costs of energy. This is a summary of the level size costs for biogas as well for offshore wind, onshore wind, etc. And what you can see, especially for fixed, the level size costs are quite high. And to reduce those level size costs is a target. It's a need for the next years to produce offshore energy in a cost competitive way. And this is the summary of the real data. And when we are looking to floating offshore wind, the developers publish several datas, and this can be seen here. So we are working around 6 euro cent per kilowatt hour, and this is quite nice because it's cost competitive to fossil energy sources, as well to onshore wind, where it is already. But to reach this aim, we need to take into account the lessons learned from fixed offshore wind, especially from the substructure optimization, etc. So what you can see here, fixed is dominated by monopiles, and monopiles are dominating the fixed solution or the fixed offshore wind market because of the simplified structure, because of the simple solution which is provided by those monopiles and fabrication point of view, etc. So meaning, if we are going the way of taking the lessons learned from monopiles, bringing them to floating offshore wind, you can go the way to become cost competitive. Meaning, it is a need to simplify structures, and especially when we are looking to the number of structures, it's quite difficult to do it. Because there are a lot of developers on the market, we have a lot of different solutions there. But what we know, the floating solutions normally are normally those solutions having buoyancy bodies available, cylindrical buoyancy bodies. So meaning, if you simplify those solutions and looking which components can be used for, or which are used for different floating substructures, you can go the way to reduce the costs, because you can take those components for several solutions. And in the end, this was something which is under investigation, because normally floating offshore wind is based on typical and classical ship fabrication technologies, so bringing in a lot of stiffeners, etc. And this is something which need to prevent in the next years, and which need to be investigated to reduce stiffeners to a structural solution without stiffeners, etc. And there is, for example, one solution which is going this way already. This is a floating substructure from Mr. Stiesel, which is shown here. So he combined pipes without stiffeners to a floating substructure, which is seen also on the next slide. So you have the yellow one. It's a substructure shelf, and the let's say orange brown one here. It's a lower part of the substructure. In another way, you can, for example, design cylindrical buoyancy bodies based on monopile technology. So designing a solution without stiffeners, as it is presented on this slide here. So no stiffeners inside, having only a bottom and a top plate in combination with the center pipe, and taking this as a so-called universal usable buoyancy body for different floating substructures to reduce the costs in the end. This brings me to the summary. Based on those simplifications and using components which can be used for different substructures, costs can be saved, and bringing floating offshore wind to a cost competitive solution for the next decade to provide offshore electricity. Okay, that's it.
Thank you so much to being perfect in time, because we have exactly 20 minutes left for the last talk. Is there an urgent question to Frank Adam? If it's not the case, of course, yeah, okay. Thomas Schädel, can you?
We cannot hear him.
We cannot hear you.
Microphone is off. No, maybe you can hear me. Sorry.
Yeah.
Yes.
Okay, perfect. So, very, very interesting talk. I like this very much, because I didn't realize how these big units, these windmills, are fixed in the ocean. Do you have any idea, or can you tell us how the electricity is coming to our cities from the ocean?
Yeah. So sure, there are grid issues. This is more or less an famous issue we have. We know it from Germany, etc. So that is especially also part of the strategy in Scotland. So more than 50% of this electricity capacity, which is under investigation at the moment, should be used to produce hydrogen and or more. So that is per default part of their strategy.
Okay. I see.
So let me stop this here because unfortunately we are quite tight, and I will overhand to my colleague Angela Kut, which is a speaker and coordinator of the Campfire project, a big project dealing with ammonia from wind and water as a maritime fuel and energy storage. And I will hand over to her. I will switch off my microphone, but I will then also change the transparencies here.
Hallo, can you hear me? Bin ich zu hören? Ja, okay, gut. Ja, erstmal herzlichen Dank. Many thanks for the opportunity to speak here, and I'm very, very pleased to see quite a few known faces and also old friends, not old, but hello, Thomas. We didn't manage to catch up for a long time, so I'm very happy to see you here in the video chat. And I'm very pleased to also introduce you to our current activities in the Campfire Alliance, which was founded roughly a little bit more than 2 years ago, now within the frame of the BMBF initiative, Wir Wandel durch Innovation in the region. And Skip, I have to apologize in advance, skip through quite a few slides here, possibly because of the limited time. So first of all, I'm going to say a few things about green ammonia. I'm very sure in this audience, I don't really need to introduce ammonia anymore. This has already been done by Thomas and also by Herrn Abel. Many thanks. So I'm going to not spend too much time on it. Then I'm going to report on the current projects and the Campfire projects, which are carried out at the moment, and also some new activities we have within the lead projects of the BMBF, then the Wasserstoff Republik Deutschland initiative in the Transheit cluster. We just submitted 36 projects there last night, so I'm a little bit, haven't slept much, but it's all done now. Okay, so why green ammonia? It's carbon free. So that's really the main reason we focused on green ammonia after 7 months of concept phase in Campfire in 2019. It's carbon free, so we basically don't have the problem of the availability of carbon, also the cost of extracting carbon from air or from industrial streams. Sebastian has already discussed that very deeply, and also demonstrated the problem we have with biogenic CO2. So if we really want an energy transition and if we want it fast, we need to get away from the drug, like we call it, carbon. And of course, nitrogen is also an atom where we can hook up hydrogen to and also achieve a fuel that is highly dense, or comparably to other fuels, quite dense. And as you see here, even compared to liquid hydrogen, it contains more energy than compressed or liquidized hydrogen here at very low temperatures, as opposed to minus 33 degrees for ammonia. And this is due to the structure of the ammonia molecule that actually contains more hydrogen than liquid hydrogen itself. And so we have a high energy density, which we can achieve at relatively normal pressure or like a refrigerator temperature. And so, Dirk, schaltest du die Folien? Ich kann das nämlich auch machen, glaube ich. Gut, wann war ich fertig? Yeah, and also one of the biggest advantages is we already have an infrastructure, and we have over 100 years of experience in handling ammonia and transporting around the world. Again, quickly shown here, it's not only have advantages with regard to energy density and storage properties, it's also cheaper to liquidize ammonia when we basically refer to the electrolysis of hydrogen here and take into account all the steps, including the synthesis of ammonia and then the liquidation. We come out with a much higher efficiency from well to wheel as opposed to hydrogen. Ja, okay, es klappt. in comparison to other synthetic fuels, which we have discussed today. Okay. The carbon-based new fuels like methane, methanol, or also dimethyl ether. You see here the power to fuel to power indices. So again, a large advantage, mainly due to this fact that we extract nitrogen from air. We have it present at very high concentrations. It's abundant, and we also have some advantages with regard to the synthesis. So we come out with the highest power to fuel to power indices as compared to the other synthetic fuels, and it's carbon-free. Okay. So a big game changer last summer was the announcement by Air Products and Halder Topsoe with some other partners that about the start of a very large project in Saudi Arabia. So the largest hydrogen electrolysis project worldwide. And what do they do? If you go to the next slide, they basically produced ammonia in Saudi Arabia. You can see here the location in the slide, and distributed around the world to mainly for heavy duty landside traffic. And the way they basically distributed or transported economically is via green ammonia. So this is the largest electrolysis project, like I said, worldwide, and the aim is really to supply green ammonia around the world and including Europe by 2025. This is a 7 billion investment here, so it's a very large scale. For maritime mobility, also there has been a lot of effort put into LNG over 15 or 17 years. It took a long time to basically get it, also to get all the legal procedure done. So there has been a lot of investment, like I said, to basically also into technologies which can then run on LNG in order to really address the very, very bad need of the maritime industry to decarbonize shipping. In recent years, increasingly ammonia is seen really as the only way to really fulfill this aim. Of course, this will be in combination with other fuels. We also have developments in methanol, and we are sure over the next years it will be a mixture. There will be a transition period, but from 2030 onwards, ammonia is seen as the maritime fuel of the future. So you see big engine producers like MAN or Wärtsilä, who already have been working for a few years on ammonia, large-scale ammonia combustion engines. They start basically also being a bit more visible about it. There's a few projects now known as a European project, which started a few years ago, is now going into the second phase. And also MAN, who developed with the TU Denmark, the two-stroke green ammonia engine a little while ago. They're also now working in a new consortium with a partner from Rostock, together also on the four-stroke ammonia sea vessel engine. So our Campfire Bündnis is an alliance of around 40 partners at the moment, and our vision is to develop, first of all, technologies for seasonal, I don't want to say small scale, because it's not quite clear what small scale is. If we talk about gigawatt scale, like Adam just in the previous talk, so seasonal and regional production of ammonia from air and water, and this will be in addition, of course, to import of ammonia, which we have to, of course, and also take into account. Roughly, the estimations are that 80% of the hydrogen which is imported to Germany will be 80% of the need we have will be by imports, and around 20% we still need to address really fluctuating demands, seasonal demands, which would be too expensive to realize that by basically imports and realization of a base load. So for the average to increase really the supply and the we will have to also combine the import of ammonia with regional and seasonal production. And for this, we need very flexible and also relatively small scale compared to the normal Haber-Bosch processes, so small scale technologies to produce ammonia on a also economic scale. And on the other focus we have in Campfire is then the technologies for utilization of ammonia with a focus on maritime drives, as shown here in this graphic. So yeah, just at the moment, like I said, we have 40 partners. Just going to skip through this. You can see that also on the website. So these are our technologies or our technological pathways at the moment. In the first phase of Campfire, we focus, like I said, on the small scale production using solid oxide electrolyzer cells in combination with a micro Haber-Bosch process in the first path here. And then for utilization of ammonia, we develop ammonia cracker, also of course the materials, the catalyst for that, and combine it then with a combustion engine, which are usually at the moment used for BHKW, for combined heat and power, for stationary power generations, but these are the engines which are suitable really for combination with a cracker. And the challenge here is to demonstrate or to realize the dynamic you need on board of a boat. And above all, of course, also safety issues. We need a good safety system to account for all Havari cases or emergency cases which we have on board, and also, of course, concepts to train the personnel to deal with the new technologies and with ammonia on board. And you see the second path here called Lösungsweg B. Here we have technologies which are a little bit more challenging still. Also, they won't be probably not be suitable for transfer really within the next 2 years. So they're still lab-based, the basic research, and but however, if we are successful, then it means this will be quite a big step improvement with regard to the efficiency of technologies and also lifetime. So here we develop the solid-state ammonia synthesis as a direct electrochemical methods for ammonia production. Membrane-based ammonia cracker, which has, we hope, an advantage with regard to the flexibility and also fast startup shutdown, and also addressing loads on board, and also the high temperature fuel cell, which where we have a thin film approach, which we developed together with partners in NRW. Within those paths, we have quite a few projects allocated, as you see here. I won't go through them all. So these are our basically main product categories which we develop. And at the moment, we have basically halfway through, and our next phase in Campfire basically starts beginning of next year. So for the next year, we need a new strategy, basically to focus a little bit more and select pathways which are then also leading us into transfer. So for the first thin layer projects here, solid-state ammonia, you see the partners here together with the Likert in Rostock, ZBT in Duisburg, Fraunhofer IKTS in Hermsdorf. We developed the solid-state ammonia device. I won't go through everything we go now. So it's based on a porous tube, thin layer deposition, catalyst development, and then also stack production by the ZBT. We develop oxygen permeation membranes to improve the cracker, like I mentioned before. Also, again, here a thin film approach to improve efficiency and cycle stability in the same partner round. The green ammonia reactor is a project with the KIT, the colleagues there, ZBT and University of Rostock, and Yara and MET, where we use a design by the KIT, which is used for SO2 oxidation. This is like SLA, selective light elemental reactor. This microelements here realize a graduate temperature profile, and we hope to be able to decrease the temperature and also the pressure of the Haber-Bosch process, and realize a flexibility. Next running project is the maritime mobility. Here we show, together with those partners you see here, a combined cracker, gas motor, SOFC power generation device on board of a small yacht to start with. This boat will be up and running around 2 years from now, and also serve to, that we learn from it. We can do upscales, we can do modeling, and prepare basically the upscale of the technologies for the large scale projects. Genau. Da ist noch einer, fehlt noch. So we develop also a cracker gas motor combination from inland ferry in Rostock, which is basically like a passenger ferry across the river Warnow with a 350 kW combustion engines which is used usually for stationary power generation, and in combination with the cracker by the ZPT, and like I said, all the other components we need on board of the ship. And finally, the Green Baltic Cruising Project, which is basically still paper-based, together with also Carnival, is interested in looking at first Baltic Sea route based on green ammonia on a combination of a cracker with a polymer-based fuel cell. So this enables a big new chance really for our region in Mecklenburg-Vorpommern, and also not just for our region, but also Germany-wide or Europe-wide. When you look at our map, you see we have really amazing advantages. Of course, we just heard us talk about Scotland and the offshore wind generation, which is of course another scale again, but even near our own coast, we have potentially in future a 4 gigawatt, one of the very few gigawatt generation points of Germany. And we also have a chemical factory here, a fertilizer plant from Yara, one of the large hydrogen utilization plants. Ammonia is the largest hydrogen product or hydrogen-based product worldwide. So this is basically near Rostock, 6 kilometers from the harbor. We have the sea ferries here, of course, and we also have to address really security also of supply, the possibility to generate the turquoise hydrogen, which is not really what we want in Campfire. We really are 100% green, but we all know that it's not really possible over the next year to convert to 100% green. So we need, for security of the demand, also some intermediate solutions. When we look at Rostock as a possibility here to bring Rostock into, to make it CO2 free by really a pure green supply of renewable energy, we need to address for the Dunkelflaute. If we take into account, we want to basically provide energy for a Dunkelflaute of around a week. We need hydrogen storage of 1,522 tons. If you take into account that the number you see here for Rückverstromung, for reconversion of a yield of 50%. This correlates to a hydrogen storage tank of, for instance, 60 bars, which is quite low, but this is just a value we use for. We see sometimes as in proposals. We need a size of 2 football fields times the height of the Petri Church in Rostock, so a very large volume, which comes to very high cost of around 460 million euros invest. If you're familiar with hydrogen storage tanks based on carbon fiber, they don't last long. They last at most 10 years. And you also need to take into account, of course, that it's not like one large storage. Of course, they are 40-feet containers and they need to be connected. So on top of the price I show you here, you can really double that price to come to the real cost really of that, what this hydrogen storage basically would mean in money. Compared here, the ammonia storage of the same amount of hydrogen, you need a 32-meter diameter tank, 22-meter height, and much lower investment cost of 20 million. So you see the massive really advantage ammonia has for transport, for handling, for storage, and also price-wise. So in the the hydrogen Leitprojekte, Wasserstoffleitprojekte of the BMBF. There was a call last summer. We put a proposal in for developing research and topics within really opening up the path for ammonia as a possibility to transport hydrogen, so B2B and economic transport solution, and located here again 36 projects, which we submitted last night, like I mentioned earlier, to realize basically the whole ammonia ecosystem in the region of Rostock as a starting point. So the power to ammonia line basically to transport. You need refueling stations, you need innovative systems to really transfer from one pressure to the other pressure, or to change temperature, and also to work in an autark way on different scales, and also the back conversion then into energy or into hydrogen. This is an overview of the projects we submitted here, and you see here this sketch from our partners, the ICEM, Institute für Klimaschutz, Energie, Mobilität, who basically sketched out the first infrastructure and logistic chain, starting in Rostock as one point. Of course, we also have Lubmin as a second, much larger generation point. And not only distributing, as you see here, in Germany and into southern Germany, but also, of course, a network across the Baltic Sea. Even though we know that in not many years there will be a lot of green ammonia coming from cheap Norwegian and Swedish electrolyzers, where with much lower basically hydrogen prices than we can ever realize here. But as I said, for regional generation, there is a business case for the seasonal supply, so that's where we still see our role.
Maybe you can speak up a little bit, Angela. Yes.
Yeah, I'm almost finished. So to develop these technologies and to test them and bring them to transfer, we need also a good testing facility. We need cheap supply of media. We need the industry environment there, and this is what we have with the Yara industrial site near Rostock. Like I said, there's a 6 kilometers from the industry harbor, connected by an ammonia pipe, which is basically underground. And here we can use an area for the TransHyd project. We got about 30 million for the entire project and 12 million to develop the site. You see here a site of 12 hectares, which we will develop over the next 2 years as a green ammonia site for testing new technologies such as maritime drives, combustion engines, fuel cells in combination with large-scale crackers, as well as decentralized ammonia production in combination also with solar thermal. That's one project we also at the moment are developing with the industry partner. And this is what this will be called the COIL Campfire Open Innovation Lab, where we do some research, but very applied labs and in connection as a focus really to realize technologies for the new green ammonia ecosystem here. And we would really like to collaborate on this with our partners and research partners. Also, we already are collaborating. Herr Abel, we're really looking forward very much to the start of our project. Hopefully it won't be too long. So this will be very exciting, also for landside traffic, of course. And we hope we can basically, we're very much looking forward to getting started. There's a lot of activity all in parallel. And this is, sorry, kann ich das machen? Ich weiß nicht, warum das hier durchblättert, Dirk. Ich mache nichts. Ich war eigentlich schon fertig, aber I was finished, aber irgendwie rollt das jetzt zurück.
Thank you so much. So the official end of the session was already 4 o'clock, but I think there might be a 10 minutes break up to the next session and the invited speakers there. So maybe we have 3 minutes in addition for some discussion. So I already asked the participants, is there some urgent or question to it? I think there's no question from the audience and also not from the speakers. Yeah, because we are even quite, yeah, Mr. Schädel.
Yeah, hello, Angela. Wow.
Hello.
Very impressive talk. Thanks so much. And coming now a little bit to the basics. Okay, we are physics, right? what is the idea? What is your fuel cell, your electrolyzer? So what is the material? Can you give me some insight in what is really going on in your reactor, in your electrolyzer to have ammonia at the end? I mean,
We use
this, right? It's a scientific question. If you have a, you can show.
That's fine, yeah. The solid state ammonia synthesis may be done with oxide ion conducting membranes, but we use proton conducting membranes to be able to lower the temperature. And you also have no dilution of the ammonia with water. No? You can produce directly anhydrous ammonia. So biom-serate zirconate-based thin films, and we put it on a at the moment state-of-the-art porous tube, which is produced by the EKTS, and it's a normal SOFC cathode material. The challenge in that and the catalysts are developed by our partners from the LICAT, which are similar to Haber-Bosch type catalysts.
So iron, iron nitride.
We go for, in this project, we use ruthenium-based catalysts. Of course, for upscale, we have learned precious metal is it's a problem, of course, but we hope with a small loading, it will, and also the possibility to be able to recycle it, we can make a good start. Yeah?
Okay.
So let me officially stop this session here because the time is over. Let me mention that the room is still open, so we can prolongate a little bit with the discussion, maybe also with seeing ourselves here. So let me thank you again, all the speakers. From my point of view, it was a very interesting session here. And thank you all. And I want to stop this here officially. I also stop the recording at this point.